going to be working on homework for 11.1. I'm going to be doing numbers 1 through 12. I've got a new microphone today, so I hope this first video comes out okay. I tested it out at home and works good, so I'll see how it works in this room. Hopefully there's not too much of an echo. Alright, so we're going to do number 1. Number 1 says, oh, and I'm also recording at a higher res, so the quality of the video hopefully will be a little better. It gives you g of x is equal to cosine of, g of xy is equal to cosine of x plus 2y. And for part A, we're supposed to first just evaluate the function. So plug in the ordered pair 2, -1. So let's do that. When we plug in 2 for x and -1 for y, we get cosine of 2 plus 2 times -1 is -2. So that's just cosine of 0. Cosine of 0 is 1. For part B, we're asked to find the domain of this function. So in terms of the domain of g, we notice that cosine, the domain of cosine is everything. So you can plug any real number into cosine, and that means that these right here, x plus 2y, right, can be anything. And so our domain is everything, right? I can let y's be 0 and then let all my x's be whatever they want, or I can let x be 0, let all my y's be whatever they want, and let x be 1 and let the y's be whatever. So it does not matter what I plug in for x or y, domain is everything. So how do we actually state that? Well, you can say x is an element of the real numbers and y is an element of the real numbers. I'm actually going to try and describe what this is geometrically. So I'm going to sketch the domain. The domain would be any point in this space. So it's the entire space, two-dimensional space. So we can just say R2 is the domain. All right, so that's it for that. How about range? Well, the range is everything that could possibly come out of this function. So remember, cosine is bounded between -1 and 1. We just need to make sure that we actually attain every value. So if you just let y be 0, cosine of x, you know, if you let x be a real number, that's going to graph the entire cosine function. So you're going to get all the outputs, all possible outputs out of this function. So you will get everything from -1 all the way to 1. So the range of this, I'll put ran at ran g, is going to be the closed interval -1 to 1. And that's it for that. Number 2, we just have a different function. So hopefully this one will be a little more interesting. Capital F of x, y equals 1 plus the square root of 4 minus y squared. It's a function of 2 variables, but x does not appear here, so that means x is free in this problem to be whatever we want. Part A, we want to evaluate f of 3, 1. So we plug in 3 for x, there is no x, so square root of 4 minus, we plug in 1 for y, so we get 1 plus root 3. That's it. Now notice that we get the same value for any value. The same value here, even if we change the x value to anything else, we get 1 plus root 3. So you can go -5 if you want 1. So what I'm saying here is that the x has absolutely no impact on the function, the x coordinate of the point. Part B, what's the domain? Well, we do have to be a little bit careful here because we have a square root. We can't have that be negative. So we need to make sure that 4 minus y squared must always be greater than or equal to 0. And that means that 4 must be greater than or equal to y squared. And then you go through, this is a quadratic inequality, you can figure out the solution set for this. It's basically everything between -2 and 2, inclusive, so including these two endpoints. These are what your y values are allowed to be. So in terms of, what the domain is, you can pretty much say y is an element of the interval -2 to 2. And your x, of course, is free. Now, picture of this would be, you have your y value has to be between -2 and 2. Remember, our domains are always in two-dimensional space. For a function of two variables, our domain is in two-dimensional space. I can have any y value between here and here, and my x can be anything. So it's going to be, imagine these lines, oops, I missed it. It's supposed to go right there. It can be anything in here, including the edges, okay? So it's like this strip that goes through your plane. Right, now for range, the range is going to be a little bit more difficult. So the range, what we're talking about, is what comes out of this. So what could possibly come out? Well, let's take a look at this square root here. The biggest that could ever be would be 4, and that would be if y is 0. And so we know that the square root of 4 is 2, right? And then 2 plus 1 would be 3. So I know right now that 1 plus square root of 4 minus y squared, that must be less than or equal to 3. Okay, so there's no way it can get bigger than 3. And then what's the smallest it could be? Well, the smallest that this could be here, the square root, would be 0 because you can't put a negative in there. So the smallest could be a 0, and that would happen if y was 2 or -2. If this is 0, then plus 1 would be 1. So the absolute smallest that could ever be would be 1. And so the range is all the stuff between here and here. So the range of f, ran f, is going to be the interval 1 to 3. So those are the only outputs that function can produce. All right, we'll look at 3. I better pick up my book for this one. You have a function of 3 variables. F of x, y, z equals square root of x plus square root of y plus square root of z plus natural log of 4 minus x squared minus y squared minus z squared, and that's it. So first for part A, they just wanted to evaluate what's f of 1, 1, 1. So now pay attention here. Notice that what we have is a function of 3 variables now. That means that the domain is in 3-dimensional space. The output is in 1-dimensional space, so we need 4 dimensions to visualize this. We can't draw this picture. But the domain is living in 3 space as opposed to the previous problems where our domain was in 2 space. So just be aware of that as we proceed here. So let's plug in this ordered triple here. We get square root of 1 is 1, square root of 1 is 1, square root of 1 is 1, plus the natural log of 4 minus 1 minus 1 minus 1. So we get a 1 plus 1 plus 1 plus the natural log of, this is 1. Natural log of 1 is 0, so you just get 3. So f of 1, 1, 1 is 3. So if you go out, you imagine you pick a point in three-dimensional space, 1, 1, 1, you plug that into some function which you can't see, and it spits out the number 3. So part B is, here they just want the domain. The ranges are hard, or can be kind of hard on these. All right, so the domain of little f, let's talk about it. First of all, we have square root of x, square root of y, square root of z. All of those can never be negative. So we need that x must be greater than or equal to 0. We have that y must be greater than or equal to 0. We have that z must be greater than or equal to 0. So right away, you know from this, in three-dimensional space, if your x, y, and z all have to be greater than or equal to 0, then you're going to be in the first octant. Right? Or you could also live on the actual coordinate planes. So you could be on the, let me draw it here. This is x, y, and z. So we have to be out here in this first octant. But you could be down here on the floor, right? That would be z is 0, you'd be down on this floor. You could also be along this edge, this wall, the yz plane, because that would be x is 0. And you could also be along this edge, which would be the xz plane, that would be when y is 0. So it's the first octant along with the actual coordinate planes that run kind of adjacent to that octant. Okay, so that's so far. Now we still have this. Now natural log, when you plug something into the natural log, the argument has to be a positive number. You can't plug in 0, you can't plug in negatives. So we have this additional restriction here that 4 minus x squared minus y squared minus z squared must be strictly greater than 0. And if I move things around, I move that variables to the right side to make them positive. We can recognize this, hopefully, that if this was an equation, if it was, that this would be a sphere of radius 2. And what we want is less than. So that means that we want all the points that are inside the sphere of radius 2. So these are all points inside sphere radius 2. And along with the fact that we have to be in the first octant, this is really all, the final result here is that the domain is all the points inside, not on the edge, okay, just inside the sphere of radius 2, but also in the first octant. So it'd be like taking like 1/8 of a ball, and that 1/8 is that one part that's in the first octant. Take that 1/8 and just all the points inside the ball, but not along the edges, but along the flat surfaces. Okay, that would be okay. So I don't know what that would look like, something like this. I don't know if that makes sense, but that would be it. All the points inside, including this edge, the bottom edge, and that back edge. But again, you couldn't be on this curved surface. You have to be right inside of it. All right, I'm going to let you do number 4 yourself, and I'm going to move on to number 5. Says to find and sketch the domain. So f of x, y equals square root of 2x minus y. So we're back to a function of 2 variables here, and we're trying to find the domain and sketch it. So remember, the only problem we have here is possibly that 2x minus y that has to be greater than or equal to 0, which means 2x has to be greater than or equal to y. And if this was an equation, if it was, this would just be 2x equals y. And if I graph that, it would be a line with slope 2 going through the origin. So up 2 over 1 would be this line right here. Whoa. That's this. Now, to figure out what this means, we just have to figure out if we're shading the top of the line or the bottom of the line. So we can just pick a test point like this one. Pick the point 1, 0. Plug it in here and see if it's true. So if I plug in 1 for x, I get 2. And if I plug in 0 for y, I get 0. And this inequality is true since the point here does satisfy the original inequality. That means this side of the line is shaded. So it's all the points over here on this side. And we also do include the line itself because we had equality inside that inequality. All right, that's 5. I thought 6 was worth looking at. We have square root of xy. Number 6. All right. Keep in mind that all of these functions here, if there's 2 variables going in, then these are surfaces. You know, we could graph just like, I don't know what they look like necessarily, but imagine you've got like a blanket or something up here, right? The domain is down there on the ground, and that's what we're trying to do is just take a look at a picture of the domain there on the ground. All right, so what do we need here? Well, again, for the domain, we know that what's in here, x times y, must be greater than or equal to 0. Well, think about what you're saying here. 2 numbers have to multiply to be greater than or equal to 0. Well, that means that both of these numbers are either positive or both of these numbers are negative. So we have this. We have that x and y are both greater than or equal to 0 because if either one of them are 0, this is true. And then you say, or x and y are both less than or equal to 0. So let's look at this first one in 2-dimensional space. If both your x coordinate and y coordinate are both greater than or equal to 0, then you have to be over here in the first quadrant. And you could also be along the y or x axis. And then if both the x and y coordinates have to be negative, then you have to be over here. And you could also be along the x-axis or the y-axis. So your domain is basically this shaded region, and the coordinate axes. It's kind of cool. All right. How about number 8? Let you do 7 on your own. For 8, f of xy equals square root of y plus square root of 25 minus x squared minus y squared. All right. So let's start with the square root of y. That tells us that y must be greater than or equal to 0. Okay, so we've got that. Now over here we need this, 25 minus x squared minus y squared, to also be greater than or equal to 0. And if we move things around kind of like we did in the previous problem, we'll notice that if this was an equals, then this would be a circle radius 5. And what we need are all the points inside of that circle. So, and also the edge we can include because the equal there. So if I'm going to go try and draw this domain, what I want to do is I want to draw a circle radius 5, and I'm going to want all the points inside of it also. But my y coordinate must be greater than 0. So when I go to draw my circle, radius 5, my y can't be negative, so I've got to be up here, here, and everything on the inside of that. Okay. Next, 9. 9's cool. I'll let you do 9. 9, just be careful because you also have division. You could possibly get division by 0. Let me see if I should do 9. Nah, I'll do 9. Why not? More fun for me, right? 9 is f of xy equals square root y minus x squared over 1 minus x squared. All right, so let's talk about the root first. First thing we need is that y minus x squared must be greater than or equal to 0. That means y must be greater than or equal to x squared. And to figure out what that is, if it were an equals, we know what that looks like. It's a parabola like this. And so what we need to do is figure out whether or not we're going to shade on the inside of the parabola or on the outside. So we just pick a test point. I can pick the point 0, 1, right? That's 0, 1. And plug it into this inequality and see if it's true. So if I plug in 1 for y, is it greater than or equal to 0? That's true. So that means that point works, which means everything inside that parabola will be shaded. That's what this one says. That's the domain. But the denominator, we need that 1 minus x squared cannot be 0, right? That means that x squared cannot be 1. So x cannot be positive or negative 1, right? And so x equals 1 is a vertical line, and x equals negative 1 is a vertical line. So what we had here is something like this. This is a little harder to draw, but my domain, my final picture of my domain would be, here's 1, here's negative 1, and let me get this, well, here's 1. So I would draw my parabola up, right, and when I get to x value of 1, I can't be that, and then I keep going. And then the same thing over here, I come up like this, when I get to 1 here, negative 1, I can't be negative 1 on my x, and then it keeps going like that. But it's everything in here shaded, but not on this line. So I can't have that piece. So it's shading everything in between there, and then shading this outside, shading this outside. So just imagine this right here, this parabola, everything on the inside, and just kind of come in here, just cut out just that single line at x equals 1 and negative 1. Cool one. All right, 10. Arc sine, x squared plus y squared minus 2. I'm going to write it a different way. Arc sine, x squared plus y squared minus 2. Just a second. brush towel. They start to stink after a while. All right, so hopefully you thought about this one while I was gone. Arcsine is an old trig function from pre-cal, and it had a domain restriction. If you're going to try and figure out what arcsine of, let's say, x is, then we had a restriction that x had to be between -1 and 1. That was an absolute restriction for arcsine to be defined. So with that in mind, what we know is that this argument in here has to also satisfy this. So that's what I'm going to do. I'm going to say that x squared plus y squared minus 2 must be less than or equal to 1 or greater than or equal to -1. And now just take this inequality, add 2. So add 2 here, add 2 here, add 2 here. So when you add 2 here, you get 1 less than or equal to x squared plus y squared is less than or equal to 3. All right, so see if you recognize this. If I just look at this, this is a circle, right? If it was equals, it would be radius 1. I want all the points bigger than that. So if you imagine a circle with radius 1, I want all the points on the circle, because it's equals, and all the points bigger, so outside of that. But then if you look at this, that's a circle, and if this was equals, then that'd be a circle with radius square root of 3, and I want all the points that are smaller than that. So if we go out to root 3 and draw a circle, well, that's terrible. I want the points inside of that. So it's going to wind up being this thing that looks almost like a washer. Okay, that's our domain. I think I'll, well, no, let me do 12, since 11's an odd one. Let me do 12. For 12, we have a function of 3 variables. And we still are asked to sketch its domain. And so I'm going to have to draw a 3-dimensional picture to be able to answer this question. 16 minus 4x squared minus 4y squared minus z squared. So what is it that we need to have happen on that one? Well, it's a natural log function, so we need the inside, 16 minus 4x squared minus 4y squared minus z squared, to be strictly greater than 0. Let's see, does that look familiar to you? Let's move everything over to one side. Almost looks like a sphere, almost, except for the fact that we've got coefficients here. So what we'll do is we'll try and so go back to quadratic surfaces. If this was an equal sign, we have all 3 variables appearing. They're all squared. You have a number on this side. What we try and do is turn this into a 1. So 1, and then divide by 16 here. So x squared over 4, 4 over 16 is 4, and then plus y squared. Again, 4 over 16, I get a 4 down here, and then this one right here plus z squared over 16. And so if this were an equal sign, the question is, what is that? And hopefully you remember that this would be an ellipsoid, right? This would be an ellipsoid, and these numbers down here kind of give you your dimensions of your ellipsoid. So 3-dimensionally, gone away from my convention of graphing. Wow, I missed that big time. So this tells me that on the x-axis I have a radius of 2. The y-axis also a 2, square root of 4. And then on the z it's 4. So let me try and draw this. Okay, like this. And then of course it goes backwards, does the same thing behind here. The bottom comes out like this, like that. Basically you get this ellipsoid, three-dimensional ellipsoid. And what we want are all the points that aren't equal to that. So we don't want the actual outside of the ellipsoid as our domain. We want the inside of it. So it's almost like a solid egg, but you don't want to count the shell. You don't want the shell. You just want the stuff inside the shell. So that's our domain, right? You take a point out of that three-dimensional space, and then you can plug it in there, and that spits out some number. All right, that's it for 11.1.